So now we start to talk about or to understand if we know machine learning, then how can we solve data science problems? Okay, so we start from let's say the common classification about different learning problems and where that we were going to have different algorithms for those, okay? Such as that maybe we have the supervised learning, unsupervised learning, semi-supervised learning, etc., right? Okay, the supervised learning is where that we have the label built in for each piece of data, right? Such as that given image, we know this image belongs to cat or dog, right? So this kind of label. So when we have this kind of label, then we can easily, or maybe we try to make sure that the precise relationship between image and its label, right? Can we pick up this kind of relation? Okay, so sometimes we don't have the label, right? So where we have unsupervised learning, so here that we are going to find out different pieces of data. Maybe they are group, they can be grouped together, right? Because they do have some similarity in between, right? So this situation is that what we call the unsupervised learning, or maybe grouping, or maybe clustering, right? So this situation, just because we don't have a lot of label information, so usually the result could be very subjective, right? Like a different piece of data, okay, uh, maybe we don't exactly know how many groups, okay, they belong to. So semi-supervised learning is something in between, right? So we have some part of the data when they have a label, but some other part they don't have label. And maybe more specifically, usually we do have a small piece of data and when they are labeled, right? But for most of the data, we don't have label. Given this kind of uh, data, can we do something that belongs to semi-supervised learning? Okay, so after all, we have a reinforcement learning. Of course, it's very famous in sense of that for the AlphaGo, then actually use this part of a method to help us to find out what could be the best way to play a chess or play Go games, right? Okay, when we talk about reinforcement learning, usually we assume that the true answer, such as when we play chess or Go games, right? So we know in the end, after a few moves, right, we know some people win the game or lose the game, right? So we don't know the answer right away. We know the answer after a few moments or maybe in some delay situation, right? Okay, so that's the first thing about reinforcement learning. The second is that uh, during those moves, right? If we play Go games or chess, right? So usually we're going to see some rewards, right? Okay, such as that if we talk about how to get a good grade for this data science course, right? So that will be, we know the answer after a few moments, right? But before everything, right? So then maybe for each homework, maybe for each exams, right? So we're going to get some feedback from instructors, right? Or maybe we're going to get some positive or negative outcomes, right? So those may give us some hint about what we are going to get in the end, right? Like a good grade or not so good, right? Okay, that belongs to reinforcement learning. So just give you some close look about for each of the topics, right? So for supervised learning, right, so we do have the data coming as like X will be the feature set, right? And also Y, okay, suppose the Y is equal to certain unknown function, right? So we're going to know, well, we are going to build up, the relationship between X and Y, okay? Given a lot of data, right, we are going to build up the relationship. If we can build up the relationship, then in the end, when we receive X, we know what kind of Y we have because we can just compute the function to get the answer. Okay, uh, so after all, we have to keep in mind that supervised learning is relatively precise because we know the answer, right? So we can easily compute things like error rate or accuracy to know the method will be effective or not, right? So that's why in the past few decades, maybe, right? So we see a lot of success from supervised learning, okay? But the bad thing about supervised learning is that we do need a lot of label information. Sometimes the label information could be painful to obtain, right? Especially if we talk about big data, right? Can we easily get a large scale label data? Usually it won't be so easy, right? So that we need to rely on some other kind of, disciplines, okay? Okay, so there'll be two kinds of supervised learning, right? So depends on what kind of Y that we have. So maybe the Y could be just a finite set, a few uh, categories, right? So we're going to say it's a classification problem, right? Okay, because the label belongs to different, let's say, categorical things like between, let's say, yes or no, like a cats and dog, right? This kind of a situation. The easy situation is the binary classification when we have cat or dog or yes or no, like a two answer, right? Okay. But of course, in general, we're going to have a few more, right? Sometimes if we want to, let's say, recognize Chinese characters, right? There'll be more than just a few hundreds, right? To find the correct label for each of the characters, right? Okay, and then we can talk about regression, right? Regression is the time that when we have a y belongs to a real number, right? So for instance, if we want to predict tomorrow there'll be raining or not, right? That belongs to classification problem or maybe binary classification problem, okay? But if we want to predict, let's say tomorrow, the temperature, what kind of temperature that we have, that belongs to a regression problem, okay? Where that we want to predict something uh, to be numerical, okay? The classification problem, let's take a look about the image analysis, right? So this situation we do given the image, right? We want to recognize the image as a dog or cat, right? So even this kind of easy problem, right? We have to pay attention to, let's say, the image actually, if we take a close look, there will be a lot of pixels. Sometimes will be millions of pixels involved, right? So uh, after going through all the different pixels, those kind of rich information, then in the end we can get the answer too, right? So actually, if you know the history, right, in the old days, right, to dealing with this kind of problem, given a bunch of pixels, right, maybe millions of them, right, then to find out the true answer could be very painful, very difficult. We call this a highly nonlinear problem. Okay, and thanks to deep learning methodology, right? So these days we no longer consider this kind of a problem to be very difficult. Sometimes could be very easy or very straightforward, such as if we talk about car plate recognition, right? So these days we already see a lot of parking lot. They have the automatic car plate reader built in, right? So it's no longer very painful situation, okay? But even though we already, again, we see this slide last week, right? So when we even, let's say we want to recognize an image, there's any cat involved, right? Okay, this we already have a lot of ambiguity, right? Such a time could be the very difficult to see, right? Or maybe very, let's say, too close to call. Okay, there'll be two things they look like very similar, right? Or sometimes uh, the cat belong to actually cat picture, right? Or maybe some kind of design figure, right? Or maybe belong to some symbolic symbolic meaning, right? So all this kind of situation, right? So we're going to have the cat recognized in different meaning, right? So are we going to say all these images are there's a cat involved, right? So it's hard to make a clear cut in this situation. In this situation, that's why even as easy as a classification problem, right? We don't say it's really so easy. Okay, so if we talk about regression problem, is another situation. Okay, so we receive a bunch of data points, right? The data points will, if we want to understand the data points, sometimes we want to find some kind of hidden curve, right? Underneath the hidden curve may be the real mechanism that generate all different data points, right? So sometimes we can try to use different polynomials such that maybe we try low order polynomial or higher order polynomial to describe those data points, right? So when we use as easy as like say linear model, right? So maybe we can get something a good a summation, but a summation may not be so precise. Okay, here that the we assume the green curve is the real answer and the blue point, blue curve, or maybe blue straight line will be something that we try to predict. Okay, so from the left to the right, we're going to see when we have more and more degrees from the polynomial, we're going to see that's on the right. Actually, we see a lot of ups and downs, right? So even the high order polynomial can really go through all the different data points, right? Given the math background, we know this must be true, right? If we try very high order polynomial, we can actually go through all the data points for sure, right? But we do see a lot of ups and downs, right? Especially when the data points will have a big gap, right? Okay, somewhere on the left, right? We're going to see a lot of gap, right, between data points, right? So in those area, we don't see a very good fit, right? Because the high order polynomial will give us a lot of ups and downs, right? So that those kind of things could be very dangerous because the prediction may not be so reliable. Okay, so somewhere in the middle, maybe we consider that as the perfect situation is that we feed the data not so bad, right? And at the same time, we also make sure that the prediction is more or less stabilized, right? It doesn't change too much, right? That doesn't change too much means that when one of the data points change a little bit, right? Like we call a perturbation, right? So the result, the final model that we try to obtain may not change too much. If that's the case, we probably will have a better confidence about the model's performance. Okay, for this kind of situation, we usually pay more attention to it. Okay, so we call the model stability. Okay, model stability. Maybe you can write it down. Right, so model stability. Okay, so model stability means what? Model, okay, so model stability. So means that, okay, if we change the data, right, to be, to, let's say, if we change data to be something with a slight perturbation, right? So are we going to say, okay, the model from this piece of data, right? Can we say model change to another model, right? Would these two model very close, okay? If the answer is yes, right, we're going to say this will be a good model, means the model stability will be very good, right? Okay, so we do have to pay attention to this kind of situation. Usually, when the model has a good stability, right, usually we say this could be considered a good model. Okay, so so we can also talk about a concrete example, such as if we want to learn a class, such as about if we want to understand what we mean by sports car, right? So usually we can find some feature that can help us to describe what is uh, sports car, right? So maybe we can assume, there'll be two things that give us more information, such as, a car price, right? A price could be some specific range, right? We say it's more like sports car, right? Or that's where that we have X1, the first feature, right? The second feature, maybe we say, oh, there's the engine power, right? We're going to say the engine power will give us more information about this will be a sports car, yes or no, right? So given these two kinds of feature, right, in the end we are going to output the correct label. We try to make it as correct as possible, right? So a 1 means it's a sports car. The 0 means it's not a sports car. So given this kind of representation, right? So maybe we can draw on the two-dimensional space where that we have a few negative data, right? Some positive data belong to a sports car, right? So here that we have x-axis will be price and y-axis will be the engine power, right? So given this kind of data plots, right? Given a few data already, right? Maybe we can build up some kind of hypothesis, right? Maybe this kind of hypothesis, so-called a rectangle hypothesis. So where that we have the price belong to certain range, and also engine power belong to certain range. So give somewhere in the middle. Okay, we're going to say those belong to a sports car, right? So meaning that whenever that we have some unknown data in the future, right? When the data fall into this region, the pink region, right? So we're going to say this belongs to a sports car, right? Otherwise, we say it's a non-sports car. So they could be considered already a very simple learning model. Okay, given data, we get the answer right away, right? But we don't know exactly this kind of a model could be good enough, yes or no. Okay, so what is unsupervised learning? Unsupervised learning means that we don't have a label information, right? Meaning that maybe for this kind of piece of data, if we don't know they'll be positive or negative, can we say in the middle part, right? So they belong to one group, some outside belong to another group, right? It may not be so easy, right? But no matter what, we still try to find out, the similarity between different data, especially when we have a lot of data, when we have a data dense in the space, right? So maybe we can already pick up some close by X to own the similar label or to have the similar meaning, right? So that's why we need to rely on clustering to help us. So later in this class, we're going to talk about clustering. Okay, So here will be some example, right? So for instance, if we do have a lot of images, right? So maybe we're going to say, oh, the top row belongs to the one kind of character, right? Down to the bottom belong to another kind of character, right? So we can just simply compute the similarity to help us to find out a different piece of data may be related to some other piece of data. Okay, this famous quote about um, different different problems, or let's say supervised learning, unsupervised learning, and reinforcement learning. Okay, so actually, this quote is from Young LaCun. Okay, LaCun, Young LaCun. Okay, Young LaCun, actually, he is a very famous deep learning figure, right? And he's from New York University, where I was from. And actually, he makes such a famous quote. Okay, so probably you already know that in the history, at least in the last couple of decades, right? So people pay a lot of attention to supervised learning. I already share with you the reason because supervised learning is very easy to evaluate, right? So when we have some prediction, we can compare to the true answer because we do have the true answer, right, in the end, right? So if they match, right? So we count one. If they don't match, we count zero, right? In the end, we can count the ratio to decide so-called accuracy, right? So given the accuracy, we know what method will be successful, right? Yes or no. So that will be very simple, right? So it's a very it's a very clear message that we can judge between a good method and the not so good method, right? So on the other hand, unsupervised learning may not be so easy. Maybe I can just give you some example. You know that unsupervised learning may not be so easy to say, let's say, very uh, clear answer, right? Maybe we're going to say, okay, there will be some group of data points, right? So given this example, maybe you can easily say, right, they belongs to two groups, right? So this kind of situation will be not so difficult, right? But think about some other situation like this, right? Okay, maybe some other situation like this. Mm, okay, some other situation like this, right? So are we going to say, oh, maybe there'll be two groups, okay, the same, or maybe you're going to say three groups, right? It could be too difficult to make a clear answer, right? So that's why the supervised learning like this, right? Like a clustering could be too close to code, right? So we don't know exactly what could be the best answer right here. So that's why in the last couple of decades, right? Not so many, it could be just 10% the people working on, or maybe even fewer than that, right? Working on supervised learning. Okay, reinforcement learning is some other situation like we play chess, right? Because it's a situation that usually people recognize that as a very like AI task, right? So people do pay attention to this reinforcement learning for quite a long time, right? But actually, reinforcement learning is not so easy in the sense that we get the answer after could be a long time, right? Could be after a few moves if we play chess, right? Okay, so given three kinds of problems or disciplines, right? So the young Lacoon say, okay, for source learning, actually, we got a few information for each piece of sample, right? Okay, the label information. Okay, for reinforcement learning, actually, we get the answer, but after a long period of time, right? Which means that in average, right, for each sample, we don't see a lot of information, right? Somewhere uh, right here is the unsupervised learning, right? Actually, unsupervised learning, not like supervised learning and the reinforcement learning. That's a place that we do have a lot of information for each sample, right? So Young LaCun say that why not to pay more attention to unsupervised learning? So he actually make a comment like, okay, he say that okay, the supervised learning is the cream on the top for the top of the a cake, right? And the reinforcement learning is actually the cherry on the top, right? And unsupervised learning is actually the cake. So he said that okay, when we have a delicious cake, right? We don't just enjoy the the icing, right, and all the cherry, right? We should pay more attention to the cake itself, right, to have better understanding about data. So in a sense, I agree with him in because usually when we have a big data, right, so we have a lot of unlabeled data, right? We cannot just rely on labeled data so that we can get a better model. It's not so easy, right? So we shouldn't just rely on some other people to spend a lot of efforts and labor to help label the data so that in the end we can build a very strong model. Things like this kind of situation may not be easily uh, making sense. So, in a sense that we should pay more attention to unsupervised learning, at least that we should deal with semi-supervised learning more, so that maybe we just need to label a small piece of data, right? For others, the majority belongs to unsupervised, right? In the end, we can get a good model given such kind of input, right? If we can succeed, right, then that means it's very good, right? Because in the future, we don't have to label a lot of data to make our model to be powerful. Okay, so here just to give you some example, like when we have a learning, machine learning, right? So maybe from time to time you're going to hear the decision tree, right? So the tree can give us a very clear answer, like rely on some internal decisions, right? That we can build a model, right? Okay, the model like this is considered to be a transparent model. So transparent model. Transparent model, transparent model. Okay, so the opposite would be what? Would be the black box model. So the famous black box model will be what? Will be deep learning, right? Deep learning is from time to time we're going to have the model to be very successful, right? But we probably don't know exactly what's going on, why that we can have such a good model, right? So maybe let's say if we don't have a lot of data, if we don't have a lot of features, right? Maybe decision tree would be a good model because the model doesn't give us something very complex situation, right? We can just rely on a few decision node to get the answer, and everybody can read the model inside out, right? So that we know what's going on about our prediction. So even let's say when we know the model is not perfect enough, we can still manually tune the model to get things right, right? So it's totally different from the deep learning situation, like when we, let's say, hear the news, like say a Tesla crash in some accident, right? So we don't know exactly what kind of network inside the, the middle part of the network fails, so that we have the total, the model, the whole thing fails, right? And also we also heard about, the deep learning model may be fragile when we change the some small piece of the data, right? The result will be totally different, right? Okay, so the decision tree, in a sense, will be transparent, so that probably we don't see so much like very strange behavior. Okay. Uh, okay, so we're going to learn a knife base. Sorry, we are going to learn a new nearest neighbor, right? K nearest neighbor right away, right? We're going to maybe spend some time on Bayesian network, right? If we do have enough time. And also you heard about artificial intelligence, artificial neural networks, right? You heard about small vector machines. Maybe we don't have time for this, right? Or maybe we can also spend a few moments to talk about Q-learning, that is for reinforcement learning. Okay, so that's another part of our lecture today. Let's take another a few minutes break and come back later.